Today we are explaining the paper, When Does LeJEPA Run a World Model?
What question is the paper trying to answer?
A world model needs a representation that preserves the world's real degrees of freedom. If an encoder twists those hidden variables into a complicated shape, nearby looking points in representation space may not correspond to nearby states, and planning can fail.
So what does LeJEPA do to prevent that distortion?
LeJEPA combines two pressures. Alignment pulls representations of related observations together. Gaussian regularization makes the overall embedding distribution look like a standard Gaussian and prevents collapse. The paper asks when those two pressures force the encoder to recover the true latent state linearly. This overview shows the claim. The true latent world on the left is Gaussian. An unknown nonlinear process scrambles it into observations in the center. LeJEPA learns an embedding on the right that restores the original geometry, with only a global rotation or reflection left unresolved.
Why is recovery up to a rotation enough?
A rotation preserves distances, angles, and straight paths. The coordinates may face a different direction, but the geometry needed for comparison and planning is unchanged. This property is called linear, orthogonal identifiability.
What assumptions make that guarantee possible?
The clean guarantee assumes that the latent state is a standard Gaussian, that related states follow a stationary additive noise transition, and that the learned representation has the same dimension as the true latent state. It is a population-level result about reaching the global optimum. The transition model is especially simple to read. The next latent state keeps a fraction row of the current state and adds independent Gaussian noise for the remaining variation. Because the marginal distribution stays Gaussian, the process gives a precise test of whether alignment preserves the real coordinates.
Where do the alignment and Gaussian conditions appear mathematically?
LeJEPA minimizes the distance between embeddings of related states, while requiring the embedding distribution to remain Gaussian. The distance term rewards predictability across the transition. The constraint stops the trivial solution where every input maps to one point.
But why must the best solution be linear instead of another Gaussian-looking twist?
The proof expands every possible representation into linear and nonlinear Gaussian components. Across a related pair, a degree 1 linear component keeps correlation low. A degree 2 component keeps only rho squared, and higher degrees decay even faster. Since rho is below 1, every nonlinear component pays a strict alignment penalty.
Then what is the paper's strongest theoretical conclusion?
For this class of stationary additive noise worlds, the Gaussian is the unique latent distribution that gives the linear recovery guarantee. The forward result says Gaussian worlds for rotation or reflection at the optimum. The converse says every non-Gaussian alternative can admit nonlinear optimum instead. The two-dimensional simulations make the forward result visible. Each left-hand plot is a nonlinear scramble of the true Gaussian coordinates. Each right-hand plot is the learned embedding. LeJEPA removes parabolic, sinusoidal, and coupling layer distortions and reconstructs the round latent geometry.
Does that recovery survive beyond these simple two-dimensional examples?
The experiments scale the latent dimension as high as 1024 and test multiple learning objectives. With Gaussian latent states, SIGREG and VICREG maintain strong linear recovery across the dimension suite. The key point is not that every optimizer behaves identically, but that the predicted linear solution remains attainable at high dimension. The distribution sweep tests the converse result. The horizontal axis changes the source distribution from sparse and heavy-tailed through Gaussian to nearly uniform. Linear recovery peaks sharply at the Gaussian setting across all three objectives. Away from Gaussianity, the learned representation can preserve its target distribution while still warping the true coordinates.
Is Gaussianity equally fragile for every mixing function?
No. The curves show that some mixings and objectives degrade more gently than others. SIGREG and Info and C keep a wider high recovery region than VICREG for heavy-tailed sources. But the common maximum at the Gaussian point is the evidence that matches the uniqueness theorem.
Real training never reaches an exact global optimum.
Yes. The approximate result separates to errors and alignment gap and a covariance deviation from perfect widening. As either error grows, the bound on orthogonal recovery degrades continuously rather than failing all at once. That makes the theorem useful as a diagnostic, not only as an exact statement. The combined result panel checks the theory from several angles. On the left, observed recovery errors mostly stay below the predicted upper bound. The second panel shows linear recovery peaking at Gaussianity. The two panels on the right connect better linear identifiability with lower planning cost.
What should I notice in the control cost panels?
A cost of 1 is the ideal straight path. Gaussian encoders are statistically indistinguishable from the oracle, while trajectory-trained encoders are biased upward. The scatter plot makes the relationship direct as linear recovery approaches 1. Control cost falls toward the optimum. The robot arm sequences show what that cost means visually. The oracle path is on top. The Gaussian encoder in the middle tracks that path closely. The trajectory encoder on the bottom bends through an unnecessary detour because its representation has warped the underlying joint space. Geometry.
Does that mean LeJEPA has learned the complete action conditioned world model?
Not yet. The theorem identifies the state representation and shows why its geometry supports planning. An action condition transition model still has to be learned. The guarantee also assumes equal latent and encoder dimensions. And it does not explain how sample size or training dynamics determine the alignment and widening errors.
What is the final takeaway for someone building world models?
The paper turns LeJEPA's empirical recipe into a precise statement. In Gaussian latent worlds with the stated transition assumptions, alignment plus Gaussian regularization cannot prefer a nonlinear scramble at the optimum. It recovers the true state up to an orthogonal transform, and that preserved geometry enables near-optimal latent space planning.
So the result is powerful because it says exactly when the learned geometry can be trusted, and exactly where that trust stops.
Exactly. That wraps up our explanation of when does LeJEPA learn a world model.